Now in example 2, we want to determine the gain of our CCVS. In our circuit below, we have a 36 volt independent source supplying a potential to a 10 ohm resistor. This 10 ohm resistor is connected to a short, as well as a 4 ohm resistor, and the 4 ohm resistor is connected to a CCVS, where a voltmeter applied across our CCVS is measuring a potential of minus 7.2 volts. Now note that the positive terminal is connected to the negative terminal of our CCVS and vice versa. Thus, our actual voltage potential across our CCVS is 7.2 volts. To begin, we'll apply step 1, where we construct N meshes, where we have mesh current 1 and mesh current 2 described in clockwise fashion as follows. Step 2 is to assign our potentials consistent with our passive sign convention, such that V1 corresponds to our 10 ohm resistor and V2 corresponds to our 4 ohm resistor. We do not apply a potential across our CCVS, for that is given by the voltmeter. Step 3 is to construct N minus N sub C KVL equations describing each mesh current. We will begin with mesh 1. For mesh 1, we have minus 36 volts plus V1 is equal to 0. Step 4 is to apply Ohm's law to said KVL equation to express our voltage potentials in terms of our mesh current and resistances, such that minus 36 volts plus 10 ohms times I1 is equal to 0, or I1 is equal to 3.6 amps. Now, as we move across and apply KVL to loop 2, we have the following. V2 minus AIA is equal to 0, where V2 can be expressed as I2 times 4 ohms, and minus AIA can be expressed as minus 7.2 volts. That is, I2 is equal to 1.8 amps. Now to solve for a gain, we recall AIA is equal to 7.2 volts, or A, our gain, is equal to 7.2 volts per IA, where IA is our short circuit. IA is shared between mesh currents 1 and 2, where IA is equal to I1 less I2. Therefore, our gain is 7.2 volts per the quantity 3.6 minus 1.8 amps, or 4 volts per amp.